We're going to treat these as notes for our forces, our component forces homework. First, a child pulls a toy by exerting a force of 15 newtons on a string making an angle of 45 degrees with the floor. Find the vertical and horizontal components of the force. Really good idea to start off with a diagram that labels the forces. So we're going to imagine this is our applied force. And then we want to find the horizontal and vertical components. So here would be the vertical, and here would be the horizontal. So for the horizontal, and our horizontal component will be and now for our vertical, and this should have been added to the diagram as well. That's where our 45 degrees is. And yes, they have come out the same because at 45 degrees, both cosine and sine give you the same value. And so that's it. That's all you have to do to find the horizontal and vertical components for a angled force. Okay, problem 2. A 17,500 Newton car is parked on an incline that makes an angle of 15 degrees with the horizontal. If the maximum force the brakes can withstand is 10,500 newtons, will the car remain at rest? Explain. So again, we want to make a force diagram. Down here a little bit. So here's our car. It has weight. And part of that weight has a component going this way, which I like to call FWY. And then a component going this way, which is called FP for the parallel component. And the parallel component is what makes the car slide down the hill or roll down the hill. And then opposite to the FWY, that perpendicular component is our normal force. This is the portion of the weight that keeps the car against the ground. And then finally, we have the rope a tension in the rope that is keeping, or I guess in the brakes in this case, keeping the car in place so it doesn't roll down. So, first off, the weight of the car is 17,500 newtons. Please note that I know it's the weight because it's given in newtons. It would be mass if it was given in kilograms. Okay, so now first off, FP will be FW sine of 15 degrees. In other words, this is 15 degrees, and that angle in there is 15 degrees. So this will be 17,500 times the sine of 15 degrees. So FP will equal 4,529.3 newtons. Now, for whether or not the car will remain at rest, we have to look at the two forces that are involved with the car's motion along the inclined plane, along the hill. And basically that means doing an F net equation. So you have the brakes trying to hold it in place, working against the component of the weight of the car that would want to pull it downhill. So basically you've got 10,500 newtons, which is what they gave us for the maximum force the brakes can withstand. Subtract the 4,529.3 newtons, the component of the weight pulling the car down the hill, and our F net ends up being and so the brakes will hold. And so here you have an example of a problem on an inclined plane. In our third problem, we have a sign attached to a wall. The sign has a weight of 400 newtons. We want to know the magnitude of the tension in the chain and the thrust force exerted by the rod. So again, let's start off with a diagram. So that we can put on the forces that are present. So this will be the tension in the chain. This will be the thrust force. Here is the weight of the sign, which again is 400 newtons. Now, not obvious in this picture so far is there has to be a force working against the weight in that same orientation that keeps the sign in place? Well, the only place for that to be is the wall, and we're going to label this one a vertical component. So this force and this force can offset each other to keep the sign in place. And then we have the rod's force, the thrust force of the rod, keeping all of this out from the wall. And again, the way to look at it is vertically, the net force, which has to be those two forces, that has to equal 0 because the sign's not moving. Therefore, those two have to be equal, which means the vertical force comprised of the tension in the chain has to be 400 newtons. Now, considering the geometry, here's our 20 degrees, by the way. Considering our geometry, okay, for this angle, FV is on the opposite side over the hypotenuse, which is sine which then we can rearrange to solve for t. So the tension in the chain will be the 400 newtons divided by the sine of 20 degrees. So the tension in the chain will be 1169.5 newtons. On the other hand, if I'm considering the thrust force here, there's two ways that I can go about it. I could use cosine, and that would be Jason over hypotenuse, now that I have the tension. Or I can use tangent, which is opposite over adjacent. And so I'm going to use the tangent one this time. That would be FV over FTH, the thrust force of the rod. And so similar to what I just did with the vertical component, and so this one, and so there I have the force, the thrust force of the rod out from the wall. Now, again, all of this starts right here. Okay, the sign is not moving in a vertical sense. So the force that of the weight has to be countered by the wall. Likewise, once I have FV, it's just a matter then of using right triangle geometries to find out what the tension is and what the thrust of the rod is. And that is problem 3. Okay. Okay, for problem 4, we're back to an inclined plane. 3,000 kilogram car is to be held on an 8-degree incline by a rope in which the maximum tension is 5,000 newtons. So it's very similar to number 2. And then we're going to work through a number of steps on this. So again, let's start off with a diagram. Again, the car will have weight straight down. There'll be a component of that weight that is perpendicular to the surface of the incline, perpendicular to the hill. And again, I like to call it FWY. And then there is the, since I've written it there, I'm going to do it this way. There is the component going that way of the weight, which is the same part, P for parallel, the same part, the component of the weight that will try to make the car go downhill. Opposite the FWY, the component of the weight perpendicular to the hill, and that's why, I don't use P here because I got P for parallel, so I can't have P for perpendicular, but this will be our normal force. And then we have the rope with the tension in it. And finally, if the hill's at an 8-degree incline, then that is also 8 degrees. So it really does help to always start with your force diagram. All right, so now, unlike problem 2, where they gave us the weight of the car because it's in newtons, note that in problem 4, we have the mass of the car because it's in kilograms. And so FW, which is mg, will be the 3,000 kilograms times the 9.8 meters per second squared. So FW is 29,400 kilogram meters per second squared, which is what a newton is. A kilogram meter per second squared is called a newton, which is the measure for force. So that's the first part. Then part A, what is the component of the weight, normal, perpendicular to the inclined surface? So again, Fn will be Fw cosine of the angle, which in this case is the 8 degrees. So I'm going to have the 29,400. And if you're like, why is that cosine? Again, here's my angle. We're talking about this, which has to be equal to that. Back to Newton's third law, equal and opposite forces that keep the car in place on the ground. And that side is adjacent to the angle, and so we use cosine. And we get a normal force of, again, this is part A. Part B, what is the component of the weight parallel to the inclined surface? So FP so this one's sine of 8 degrees. So there we have part B. Part C was make a diagram. We've already made the diagram and labeled the different forces. Part D, will the rope support the car? So again, if I'm just thinking in terms of the two forces that are in line with the car's potential motion along the hill, along the inclined plane, my F net will be the T subtract the FP. The tension that the rope can withstand is 5,000 newtons. And the FP, the 491. So the net force acting on the car along the inclined plane is a positive up the incline. So rope will hold. Now you might be curious, like, well, won't that make it move? Well, this is the maximum the rope can hold. So as long as this is not going above that, the rope can still hold. The rope is not actually trying to pull the car up the hill at this point. It is simply just trying to keep it in place. And so as long as the T is greater than the FP, car will stay in place. Now, for part E, it says if the rope breaks, how far will the car have moved down the incline by the time its speed reaches 25 meters per second? So this becomes an equation of motion type problem. If the rope breaks, then the only force acting on the car is FP. And FP, which equals that 4091.7 newtons, also equals ma. All forces can be written as F equals ma, which means I can get A from taking that force and dividing by the mass of the car, which was the 3,000 kilograms. And so the acceleration of the car is approximately 1.36 meters per second squared. Now, so this is what will pull it down the hill. Now, the rope broke. Up until that point, car wasn't moving, so my VI is 0. The question is, how far will the car have moved by the time we get to VF is 25. meters per second. So I have A, I have VI, I have VF. I can use my third equation of motion. Again, the VI is 0. So rearranging, I can do that to solve for the distance. And I end up with about 230 meters. So if the rope breaks, the car starts rolling down the hill and accelerates at 1.36 meters per second squared. It'll cover about 230 meters by the time it's going 25 meters per second. Just as a point of reference, 60 miles per hour is, let's see, is about 27 meters per second. So it's not quite 60 miles per hour at that point. But it does go from 0 to 230, or it does go from 0 to 20 to almost 60 miles per hour in about 230 meters. All right, so our last problem, we have a car can go from 0 to 60 in 8 seconds on flat ground. If the car accelerates at the same rate going up a 5-degree hill, in other words, the gas pedal is pushed down with the same amount of pressure as before, how long will it take the car to get to 60 miles per hour? And unlike the problem we just got through doing, which is if the rope broke, then the car is going to be pulled downhill by the component of the weight, bringing it downhill. This time we're looking at, how much force is needed to get the car to go uphill. So I'm going to make our drawing again. And I'm going to, overemphasize my hill here just so that it makes things a little bit easier on the drawing. Again, it has weight. Weight's always straight down. There is a component of the weight into the hill, which is opposite the normal force. There is a component of the weight going down the hill, which I can put over here. And in this case, since we're applying pressure to the gas pedal to make the car go uphill, we have an applied force trying to get us to go uphill. So there we have all the particulars for when we're on the hill. Now, we could back up a step. It's not really much of a diagram, but we could back up a step. And here's my car on the flat ground. And really, the only things that we got going here on flat ground And then, of course, we have our normal force. And, this would be on the flat ground. This would be when it's on the inclined plane. The two FNs are not the same, but the FAs are the same. And the FWs will be the same because it's the same car in both cases. Now, if we just consider this for a moment, okay, our problem tells us that we're going from 0 to 60 in 8 seconds. So I have, VI is 0, VF is 60 miles per hour, which is 88 feet per second. But eventually I got to be in newtons. And so really what I needed to do was change the miles per hour into meters per second. Well, I can do that. There are 1,609 meters approximately per 1 mile. And then I need the seconds. So this would be 1 hour is 3,600 seconds. And so we end up with 26.8 meters per second for our 60 miles per hour. That's our VF. And we have to be, for all these problems, if we're going to get to a force eventually, that force is going to be in newtons. And so velocities have to be in meters per second. Acceleration has to be in meters per second squared. We have to have all our units match. And then we also have that delta T equals 8 seconds. So I could use my first equation of motion, Vf equals Vi plus A delta T. We're going to solve for A. We started at rest, so that's 0. And therefore, A equals Vf over delta T. So A is going to equal 26.8 meters per second divided by the 8 seconds, which gives us 3.35 meters per second squared. Now, we were also told that the car was 2,000 kilograms. So if that's the acceleration to go from 0 to 60, then the force, which is mass times acceleration, will be the 2,000 kilograms times the 3.35, or the applied force, will be 6,700 newtons. So this part here is going to be 6,700 newtons. Because we want to use the same amount of force to go up the hill that we were using to go from 0 to 60 on flat ground. Now, so that's the first part. Now, I need the weight of the car. FW is mg. So that's the 2,000 kilograms times 9.8. And this will end up being 19,600 newtons. My FP will be FW sine of 5 degrees. So 19,600 newtons. P is going to equal 1708.3 newtons. So this is the component of the weight that wants to pull the car down the hill. Okay, we're going to be doing this much force to go up the hill. And so our net force along the inclined plane, along the motion, that's these two forces. So that's going to equal, notice that I'm subtracting because one's going up the hill and one's going down the hill. So this is the amount of force that's actually being used to make the car go uphill. The car's engine is applying this amount of force. The component of the weight working against it, trying to drag it back downhill, is this amount of force. F net is the difference of those two forces. So now that I have that, remember that all forces can be written as F equals ma, which means then I can rearrange to solve for the actual acceleration now going up the hill. That acceleration will be the 4991 divided by the 2,000 kilograms, which will be approximately 2.5 meters per second. So another way of looking at it is when we were on flat ground, that amount of force allowed the car to accelerate at 3.35 meters per second squared. Now that we're going up the hill, we're only going to be able to accelerate at 2.5 meters per second squared. So it's going to take longer to get to the same speed that we could on flat ground because we're now on a hill. And using things we had before, our VI will be 0, our VF will be the 26.8 meters per second. We have our A, so we can use our first equation. But now we're going to solve for the time. And so our delta T will be the 26.8 divided by the 2.5, or just under 11 seconds. So what took 8 seconds on flat ground is now going to take 10.7 seconds going up that 5-degree hill. 5 degrees doesn't sound like very much, but it's almost caused a 50% increase in the amount of time to go from 0 to 60. So hopefully this will help you on your homework, but this is an introduction to doing component force type problems.